It's a great pleasure to welcome Fai Mak again to Stanford. He's a frequent flyer. Let me see. Yeah, he does get around. So Hong Kong University of Science and Technology, then Columbia, then Cornell, then Penn State, then Cornell again, and he just launched a department recently at the Max Planck Institute in Hamburg. And so I think many of you know him well, so in brief, he's really been at the center of all the exciting progress in electronic and optical properties of layered chalcogenides, starting from, I think, grad student days, realizing the monolayer limit of TMDs gives you a direct bandgap semiconductor.
Yeah, with Tony.
Yeah. Oh, with Tony? No,
yeah.
We usually don't credit the advisors. To a wonderful proliferation of correlated states in heterostructures and bilayers. And so today he'll tell us about exciting progress in Exciton Condensation. So,
okay. All right. Thank you, Harold, for the very kind introduction. And thank you for inviting me, Steve and Harold. And it's a great pleasure to be here and also discuss all the interesting physics with the colleagues here and friends here. So I will be, actually I was told that this is the open house days, and I was warned not to say anything bad about Stanford. But if you ever really for some reason don't like the nice weather here, you can consider going here, okay? Okay, so I will be talking about our sort of journey to try to realize exciton condensate in 2D, or maybe more like exciton superfluid in 2D at high temperatures. Okay, so before I get into my talk, I would like to really acknowledge the people actually doing the work. We share labs in Cornell with Professor Ji Shan, and the majority of the work was done actually by a very talented graduate student, Fang Yuan, former postdoc in our group, now in Zhejiang University, Li Guoma, and also another graduate student, Radcliffe. All right, and we collaborate with Alan McDonald's group and his student Yongxin Zheng in UT Austin, and also the BN crystals from the famous Japanese group provide all the BN crystals, so all groups doing 2D materials. All right, so my story starts about 100 years ago by the proposal by Bose and Einstein that if you actually cool down a dilute gas of non-interacting bosons below some critical temperature, you can get a macroscopic occupation of the bosons at the ground state below some Tc. Okay, and a very simple way to understand it is that to think about the thermal de Broglie wavelength, which scales as 1 over the square root of the T, the temperature here. At high temperature, the thermal de Broglie wavelength is smaller than the mean free distance between the bosons, but at low enough temperature, the thermal de Broglie wavelength becomes longer than the mean free distance, and there is a macroscopic population of the bosons into the ground state. So the thermal de Broglie wavelength actually scales 1 over the square root of T, and this condensation happens when it's roughly equal to the mean free distance, the mean distance between the particles in 3D. The Tc is proportional, the density to the power 2/3, and divided by the mass of the particle here. Okay, so it took physicists about 100 years. Sorry, actually not 100 years, 70 years to realize the first BEC in atoms, and actually that was the rubidium atoms in 1995. And the Tc at that time is really, really low. It's about 170 nanokelvin. The reason is that it's a very dilute atomic gas with this amount of density. And these gentlemen here received the Nobel Prize in 2001 after this great discovery. So beyond atoms, actually there are also many bosons that could Bose-condense, right, in the ground state. And one of the prominent candidate is actually excitons. So let me briefly introduce the concept of excitons. From its name, it's actually coming from excitations. And so usually when people talk about excitons, that you shine light on the semiconductor, will promote an electron from the valence band to the conduction band, leaving a hole or absence of the electron in the valence band. And then there's a Coulomb force that binds the electron and the holes in the system. just like a hydrogen atom. Okay, in this case. And that comes from optical excitation. That's why it's called the excitons here. And they really look like hydrogen atoms. In fact, even the energy level, the bound states, they just look like the Rydberg levels in the hydrogen atom. And you can read off the binding energy by just from the first Rydberg state and to the continuum. That's the energy difference, and it gives you the binding energy. Okay, so for excitons, the mass is a lot smaller compared to the atoms. It's about a factor of 1,000 smaller. So that when you look at this formula here, the Tc in 3D and the degeneracy temperature for 2D, that if you have 1,000 times smaller mass, then the temperature scale will go up by a factor of 1,000 or even more. And at the same time, you can also sustain a much higher exciton density compared to the atomic density scale, so that the numerator here, the N here, you can also get it to a much higher density compared to the atoms. And as a result, you may expect that the condensation temperature in 3D, in this case, to go up by many orders of magnitude compared to the atoms. Okay, so exciton BEC was proposed first in the 1960s by this series of work, and it's mostly considering optically pumping very hot semiconductor, and hopefully you can generate a high density of excitons and reach, at low enough temperature scale, you can reach the condensed state. And many experiments actually tried over the years and optically pumping excitons in semiconductors. And typically that you pump excitons in the semiconductors that have long exciton lifetime. For instance, indirect gap semiconductors such as germanium, because the electron and the holes are separated in the momentum space in the Brillouin zone, and photon for solids has nearly zero momentum by the photons. So as a result, the excitons are really long-lived in this kind of materials. And people also try dark excitons in the copper oxide, for instance. And in these dark excitons, the dipole allowed transition is almost forbidden in this kind of material, so that the excitons are also very long-lived. There are also other more recent efforts, such as looking at Coulomb-coupled gallium arsenide quantum wells, as well as 2D semiconductor double layers. And in that case, it's really separating the electron and holes in real space, so that reduce their wave function overlap, and you get very long-lived excitons as well. So you really want to have long-lived excitons, then you pump a lot of them, and you may be able to get into an exciton BEC. But so far, I can probably safely say that in this kind of non-equilibrium situation, relying on optical pumping, the signatures of exciton BEC has so far been quite indirect and controversial. And I think it's definitely lacking some direct thermodynamic or transport evidence for exciton condensates in this type of system. Okay, so as a result, I would like to introduce we will focus more on the effort of creating or realizing equilibrium excitons. From the name, it seems a little bit counterintuitive. I told you that exciton means exciting something, but then I'm also talking about equilibrium here. So what I mean here, the excitons in my definition is only a bound electron-hole pair, so that it doesn't really need to be excited. Okay. So for this reason, let me first introduce the concept of an excitonic insulator, which, as far as I know, it was first proposed by Mott in 1961, and also worked out at the theory further extended by Kaldis, Jerome, Rice, and Kong, and as well as Halperin in the following years. So imagine now you have a semiconducting material with a tunable band gap, e.g. here, this is the axis that you can tune the band gap. And if you can tune the band gap of the semiconductor to be smaller than the binding energy of the exciton, then the system actually can gain energy by spontaneously populate a fluid of excitons in the system once you reach this condition here. So once you go below the binding energy, you can populate a spontaneous fluid of exciton. It's called an excitonic insulator. Compared to a band insulator, it's also a charge insulating state, but it actually supports a fluid of mobile excitons in the system, which is charge neutral. It's harder to detect. And it's also divided into the semiconducting side, which that the band gap is larger than zero, or the semi-metallic side, the band gap is smaller than zero. And in both sides, actually, you can support an excitonic insulator with a fluid of excitons in the system. And that's also known as the BEC limit or the BCS limit. All right, so there are not many, but several excitonic insulator candidates in the bulk form. They are typically small gap semiconductors or semi-metals. I list some of the examples here. Okay, And in this type of materials, the electron and the holes, they all live in the same material. So it's very hard to make independent electron and hole contacts. I would say that it's actually impossible to make independent electron-hole contacts. And therefore, you cannot really directly measure the excitons. You can also not control the excitons, such as its density and its chemical potential. So for this type of material, it's fundamentally difficult to provide direct experimental evidence of an excitonic insulator. So I will be therefore focused on a class of excitonic insulator. We call them a dipolar excitonic insulator because the excitons, they carry permanent dipole in this type of excitonic insulator. Okay, so the building block to build this type of dipolar excitonic insulator is a monolayer transition metal dichalcogeniide, monolayer TMD. This is the structure. The middle layer is transition metal atoms such as moly and tungsten, and the top and the bottom is sandwiched by the chalcogen atoms such as sulfur, selenium, or tellurium. If you look from top down, it looks like a honeycomb lattice structure, just like graphene. The Brillouin zone is a hexagonal Brillouin zone. The electronic states of interest are also like graphene, located at the K and the K prime point of the Brillouin zone. So a simplified band structure is just two copies of direct gaps at the K and the K prime. For the pristine material, the Fermi energy, which is this dashed line here, is located in the middle of the gap. All right. So how does it work? To create this dipolar excitonic insulator, what we do here is that we put two layers of materials on top of each other with a insulating barrier in between. For instance, we put the moly selenide and the tungsten selenide with a thin layer of hexagonal boron nitride, which is an insulator, separating the two layers. Okay? And we can apply a bias voltage VB between these two layers. These two layers, first of all, it has a type 2 band alignment. The meaning for this type 2 band alignment is that there is a conduction band minimum in one of the layer and the valence band maximum in the other layer. Okay? And the energy separation between this minimum and maximum is Eg, which is the band gap of this double layer structure. Under this bias voltage, it separates the electron and the whole chemical potential, which are represented by these dashed lines here, by an amount equal to VB. Okay, so the effective charge gap of the system under a bias voltage is no longer Eg, is actually Eg minus VB, because the VB reduces the effective charge gap for charge excitations in the system. So now if you can actually, by tuning this bias voltage VB, to tune this effective charge gap to be smaller than the binding energy of the excitons, then you can actually spontaneously populate a fluid of excitons in the system, which are illustrated like this. Electron will be in one layer, hole in the other layer, and they just bond together to form this boson. Yes?
Sorry, you call it a charge gap. This isn't the energy to add charge. It's to make a dipole excitation, right?
Yes, it's not, yeah. But actually, when you are in this state, when let's say that your bias voltage is smaller than the Eg, but let's say that but it's bigger than the exciton energy of the system. In that case, in order to add a charge into the system, it takes a gap.
No, I agree there's a charge gap, but, but that's not the charge gap. That's the neutral excitation gap.
Yeah. Okay, yeah, and well, put it another way is actually that when the VB is tuned to be larger than the exciton energy, which is Eg minus Eb, you can spontaneously populate a fluid of excitons. So by looking in this picture, you can actually see that the VB is equal to the sum of the electron and the whole chemical potential, and that's just equal to the exciton chemical potential. So it's very nice in this setting, the exciton chemical potential is just very easily tuned by this bias voltage. Another way to look at that, why this bias voltage is equal to the exciton chemical potential, is to think in terms of the free energy of the device. VB is actually equal to the derivative of the free energy of the device with respect to the exciton density or the pair density, and that's the definition for the exciton chemical potential. And furthermore, we can actually add top-bottom gates to this system here. And that actually allows us to add extra electrons or extra holes into the system, and that would tune the electron-hole density imbalance. And you can think of it that it just tunes the position of this average Fermi level between the orange dash line and the blue dash line. Okay. So there are multiple tunability into the system, but the two parameters I will focus on is this VB, which tunes the exciton chemical potential, and the VG here, which would tune the electron-hole imbalance.
might be a
Yeah.
detail, but that last statement assumes you have perfect screening, right, by that first layer. Or you don't, in experimental practice, that's a pretty good description, or do you have field penetrating through, let's say, one side to the other bilayer?
Oh yeah, I'll show you the data. Actually, when it's in the excitonic insulating state, the field can actually penetrate through pretty well. Yeah. Yeah. Okay, so compared to the bulk excitonic insulator I mentioned, the electrons and holes are now separated in real space, separated into two layers. So you can easily make electron and hole contacts to each individual layer. And you can also directly control the exciton density and exciton chemical potential, as well as measure the thermodynamic and transport properties of the excitons that I'm going to show you. And as a result, you can provide direct evidence for the excitonic insulator in this system, which I try to convince you. Okay. So how big is the exciton binding energy? And I think that was first measured by Tony in 2014. So let's first consider the optically excited excitons in monolayer TMD, which we have an electron and a hole in the same layer. Because the electron and holes live in 2D space, the Coulomb field lines that are responsible for binding this pair actually lives mostly outside of the plane. And the dielectric constant outside of the plane is actually very small, so that the Coulomb interaction or the Coulomb attraction between the electron hole is weakly screened. So as a result, the binding energy for the exciton is very large. So it was experimentally measured to be about 0.4 eV, 400 millivolts, compared to the band gap, which is about 2 eV. It's about 20% of the band gap, so it's a substantial number, a very large binding for a semiconductor like this. So the very large binding actually has implications for exciton superfluidity or exciton condensation. So as I mentioned, in 2D, you don't actually have a true condensation, but you still have a temperature scale, which is called the degeneracy temperature scale, TD here. Which is proportional to the density of the exciton divided by the mass of the exciton. To maximize the degeneracy temperature, you want to maximize the density of the excitons, but you cannot get too dense because, as long as you get too dense, the excitons start to see the internal structure of each other. And when the exciton come close on the order of the Bohr radius of the exciton, then they start to get ionized. So you don't want to get them to be too close. And in fact, the maximum density is some factor F divided by the Bohr radius squared of the excitons. And if you look at this expression here, this object here is nothing else but just the exciton binding energy. Okay, so it's some factor times the exciton binding energy that will give you the maximum degeneracy temperature. And this factor was worked out by this theory paper using quantum Monte Carlo calculation to show that it's on the order of a half. Okay, so it's about 0.5. And if you plug in the numbers of a 0.4 eV binding energy multiplied by a half and you convert into temperature scale, the maximum degeneracy temperature is actually over 1,000 Kelvin. It's actually close to 2,000 Kelvin. Something. So there's plenty of room for you to reach a pretty high temperature exciton superfluidity in this kind of system in principle. Right? So this looks too good to be true, and anything too good to be true is usually not true. So what the problem is actually that the very large excitonic binding will also mean that it's very short excitonic lifetime because of the strong light-matter coupling in the system. So in fact, the light-matter coupling in this system is so strong that the light-matter coupling rate exceeds all the other defacing rates from the other channels, such as exciton phonon coupling or exciton disorder defacing rate. So at the exciton resonance, the material, even though it's just a single layer of material, it actually acts like a perfect mirror that reflects almost all the light that you shoot into the sample. This is an example here which shows the reflection contrast of a monolayer of tungsten selenide, a suspended structure. You can actually see that even though it's a monolayer of material, at the exciton resonance, it can reflect about 90% of the light in the system because of the very strong excitonic binding in the system. And you can estimate the line width from this measurement is about 5 milli-electron volt, and that is really the light-matter coupling rate, and that limits the exciton lifetime to be about a picosecond. So the very strong binding at the same time would just say that the excitons are extremely short-lived, and you don't have enough time to really equilibrate them to reach to the condensed state. So that's why we really need to put them into two different layers to insert an insulating barrier to separate the electron and the holes to reduce their wave function overlap, so that to really lengthen their lifetime and still maintain the strong binding energy. So because of this spatial separation of the electron and holes, the exciton binding energy is quite a bit reduced to about tens of milli-electron volt to about 100 milli-electron volt. But it's still substantial enough that when the theorists calculate the phase diagram for this non-interacting boson gas under this setting of a 2 nanometer separation of the electron and hole layer, you can get a degeneracy temperature still up to about 100 Kelvin and a BKT transition temperature that's about 30 Kelvin. Okay, so still pretty high temperature scale for the exciton superfluidity, not 1000 Kelvin, but still substantial. Okay. All right, so with this introduction, this is the outline of my talk. First, I will tell you how we realize an equilibrium excitonic insulator in the setting that I told you about. And I will talk about some thermodynamic evidence and also transport evidence that establish that there is indeed a fluid of excitons in the system. If time permits, I will also talk a little bit about how we can start with an excitonic insulator and add additional electrons or holes into the system and create a fluid of Trions, which is a 3-particle bound state. And I will also talk a little bit about the Trion-Hall effect. Okay, so this is the double layer structure. As I mentioned, we have 2 parameters that can tune the system. One is the interlayer bias voltage, VB. The other is the gate voltage, VG here. So by just knowing the thickness of each layer individually, we can measure, for instance, with atomic force microscope, then we can immediately simulate the electrostatic phase diagram of this double layer, which is plotted in this way. This is the VB, which tunes the pair density. This is the VG, tunes the electron-hole imbalance. And the phase diagram actually can be separated into 4 regions. So let me just walk you through. The most boring region is this II region, which means that each of the layer is intrinsic. There's no doping in both the moly layer and the tungsten layer. Okay? The IN region is that the tungsten layer is still remaining intrinsic, but there are now electron doping in the moly layer. So that's why we call it the N. N represents a electron doping in the moly layer. The PI region in this case would be that the moly would be intrinsic, but then there are hole doping into the tungsten layer. And finally, we are mostly interested in this region here, that both layers are simultaneously doped, but one by electron, one by hole, so that the band illustration is like this, electron dope in the moly and hole dope in the tungsten. 4 different regions. All right, so the first experiment that I will show is a charge compressibility measurement, which tells you whether the state is the double layer structure is an insulating state or in a metallic state. So what we do in this measurement is that we apply a small AC voltage to the top gate, DVG here, and measure the displacement current or the charge that we collect from the bottom gate here. All right, so this is called a penetration capacitance measurement because we measure the capacitance of the electric field that penetrates through the sample. So it's called a penetration capacitance measurement. And it's proportional to the 1 over the penetration capacitance is actually proportional to the charge compressibility of the entire double layer structure within this red dashed line box. So this is the data under zero bias. The Fermi level is like this. And if we, so without any, with a zero gate, well, near zero gate voltage here, that the Fermi level is living inside the gap of the material. This double layer is actually a charge insulator. The electric field that you apply from the top gate would just easily penetrate through the bottom gate, and you can collect the charge very easily. And so you get a large capacitance signal, which is actually close to the geometric capacitance of this structure here. But once you move the Fermi energy here, that would touch the conduction band minimum by your gate, then you can see that there's suddenly a drop in the penetration capacitance because the system now becomes metallic and the metal will just screen out the penetration field and you just collect nearly no charge from the bottom gate. So that's the conduction band edge. This drop is the conduction band edge of the moly. And equally, you can move the Fermi energy to the valence band maximum and that's produce another drop, and that would be the valence band edge of the tungsten layer in this case. Okay.
Can I ask, in this experiment, the middle layer that's turning into a metal, how do you ground it?
How do you?
In other words, how do you fix its chemical potential? You're saying electrons are flowing in. Maybe I'm not understanding. Are they flowing? No, it's charge. It's actually.
Yeah, it's charge. Basically, that these two layers are now kept in ground.
There is no HBN between the two, right?
There's HBN between the two.
There is?
There is HBN between the two.
What's the thickness?
It's about 2 nanometer. Yeah, 1 to 2 nanometer.
What's confusing me is that your electric fields are all pointing up.
Yeah.
But the conduction that you'd have would be sideways.
Yes, actually, you try to modulate the vertical electric field and then see how the charge would, whether it wants to move into the plane or not.
Gotcha. So where's it coming from?
From the contact.
So there's a contact to the middle layer.
To actually both of this layer, which is just not shown in this schematic. Because, this is the electron layer, this is the hole layer. We are making electron contact to this layer and hole contact to this layer.
The gate is in the middle. There's this gating thing in the middle, and then the sample goes out to a larger distance, and there's a grounding electrode.
Yes, yes. That provides the reservoir, yeah. And in fact, we actually have to engineer carefully the exciton contact in order to let the electron and the hole get in. Yeah. Okay. By directly reading the energy difference or the voltage difference between this valence band edge and the conduction band edge, that will actually just give us the energy gap of the system, which is the energy gap between the conduction band minimum and the valence band maximum. And in this particular case, it's about 0.5 eV. So half a volt, the energy difference from here to here. Okay. And that's for zero bias. You can apply a bias that separates the electron and the whole chemical potential, and that will reduce the effective charge gap. This is the map of the penetration capacitance, or if you like, the compressibility of the system, or the incompressibility of the system, as a function of VB and VG. And red means incompressible, and you can directly read out the charge gap by the energy difference, or by the VG difference, by this arrow here, basically. So with increasing VB, you are decreasing the charge gap, and finally the charge gap closes at this point, and there's no more charge gap in the system. And finally, the system becomes compressible in the blue region. Okay, so I hope it is clear. And now we can compare this map with the electrostatic simulation, and you look at them, mostly it agrees pretty well. You know, you get this II region here, which is charge incompressible because you have no charge in either of the layer, and you have the IN region, PI region here in there. It's electron dope and hole dope, so it's compressible. And you also have the PN region here, which is also compressible. But if you look a little bit more closely, you can actually see that the injection threshold for the electron and hole pairs somehow is actually pulled down by about 30 millivolt compared to the tip where the gap is closed. Okay, so compared to here, the electron hole injection threshold should be exactly aligned to the tip, but the experiment actually shows that it's pulled down from the tip by about 30 millielectron volt. Okay, so now it already suggests that maybe in this triangular region here, we actually get a charge incompressible state, but somehow there are already electron hole pairs in the system, and that would be just the excitonic insulator that I'm talking about. Okay, so that to show that there are indeed electron hole pairs in this region here where the system is incompressible, we can come to another measurement, which is called the interlayer capacitance measurement, which directly measures the exciton compressibility. So what we do in this measurement is that we apply an AC voltage of dVB to one of the layer and collect the displacement current from the other layer. All right. So note that the VB actually modulates the pair density so that the interlayer capacitance is equal to the dNx, the pair density change, divided by the voltage bias modulation. And remember that VB is actually equal to the exciton chemical potential. As a result, this interlayer capacitance will provide a direct measurement of the exciton compressibility of the double layer. So this shows an example. This is the interlayer capacitance as a function of the exciton chemical potential, or VB. On the left-hand side, there's no exciton, so that the CI is 0. And once you populate excitons, you get a finite signal in the interlayer capacitance here. And if you integrate this curve here, that will give you the red curve, which would actually tell you the exciton density as a function of the exciton chemical potential. And that's just the exciton thermodynamic equation of state. Okay, so now we can put everything together. On the right-hand side is the charge compressibility. On the left-hand side is the exciton compressibility. And remember that the charge compressibility, the red region, means that it's charge incompressible. We have a charge gap. It's an insulator. But you can see that inside this triangle, while the system is actually it's in an incompressible state, the exciton is compressible, meaning that there are really electron-hole pairs in this system. So that it really provides a direct thermodynamic evidence of an excitonic insulator, that we have a state that has a charge gap, but there is a fluid of excitons that are already populated inside this triangle. Okay. So maybe the most direct experiment is that directly flow an exciton current in the system. Okay, so in order to flow an exciton current, this is what we do here. Remember that we actually have independent electron contact and hole contact to each of these layers. So what we do is that we drive a current in the electron layer, and we measure the current in the hole layer. And this is called a drag counterflow measurement. Okay. So if you have excitons, bound electron-hole pairs, the amount of current that you drive should be equal to the amount of current that you drag in the system. So the drag current should be equal to the drive current in this situation, except that the two currents are now flowing in opposite direction. So overall, you don't actually get a charge current in the system, but you get something flowing, and that something flowing is the excitons that are flowing in the system. On the other hand, if you have no exciton binding, meaning that it's electron-hole plasma, then at low temperature, you would just get negligible drag current. Even you drive very hard if you like, but you get just no current on the other layer at low temperature. Okay, so here is the data. Again, this is the compressibility map, VB and VG, exciton of the charge compressibility. This triangle region is the excitonic insulator. And this is the drive current of the electron layer. Okay, blue means no current, red means you already start some current in the channel. And you can actually see that whenever there is an N in the phase diagram, you actually would turn on the electron layer, because that's where you dope electrons into the layer. So you get the current here, you also get current in the PN region. And on the other hand, for the drag current, you only get substantial drag current inside this triangle here. Well, there's a little bit of things happening outside, and I'll come back to that later. But you get only the large drag current inside this triangle where you support excitonic insulator. So we can make a line cut that is along the line of n equal to p, meaning that there's complete charge neutrality in the system. And we can look at how the drive current and the drag current scale with the pair density in the system. So this is the result along that charge neutrality line. The black curve here is the drive current. It gets sharply turned on once the electron channel is doped by electrons. So that's the black curve. The red curve here is the drag current, which is the current that spontaneously flow in the whole layer. You can see that once it's turned on, it's following the drive current nearly perfectly until at some critical density, which I will come back later. At this critical density, it will sharply drop to 0 drag current. So if you take the ratio, you can actually see that the ratio is equal to 1 in this excitonic insulator region, which is over this window here, that you get a perfect Coulomb drag, that the whole layer, the whole current is exactly the same as the electron current, except that they are flowing in opposite direction. Yeah.
A couple slides ago, you had showed these capacitance measurements. And so you'd integrate something up and you have this nonlinear thing. So as you're cranking up density, I presume you're crossing a BKT transition at whatever, I guess this, yeah. Is that a fair statement? I was kind of curious, where are you in the experiments you just showed? Would you be below a TBKT, you think?
Yeah, unfortunately, this exciton compressibility measurement is not sensitive to superfluidity in excitons. So you can actually see that the interlayer capacitance is very large at the beginning that you inject excitons into the system. It's just telling you that it's way easier to inject a dipole compared to inject independent charge.
Oh, I see.
Yeah.
But it's not.
Actually, it's a measurement of the exciton-exciton interaction. in some way. This exciton compressibility is measurement of exciton-exciton interaction. It's not sensitive to the superfluid phase or not. Yeah, it's not sensitive to phase coherence. Yeah.
The electric currents are flowing opposite in the two layers or the same?
The electrical current is opposite. So the exciton is flowing.
That means that there's no net charge flowing.
There's no net charge flowing. There's a charge neutral current flowing overall, but yeah.
Isn't there a momentum problem? I mean, you've got particles, let's see. Particles with opposite charge go in the same way.
Yeah, like hydrogen.
Yeah, it's you can think of it that if you want to drive a charge current, you need to apply in-plane electric field. But if you want to drive an exciton current, in this dipolar case, you actually want a displacement field gradient in the vertical direction.
Okay, let me rephrase the question. There's a physics thing I'm not getting, which is that this is neutral transport.
Yeah.
But you're measuring with charge transport.
Yes.
And so there's an unstated thing going on where the excitons form and unform at the edges or something.
Yes, at the context, yes.
Context. And then remind me why they move. Okay. There's a chemical potential that's different. You would sort of explain it, it's going by me too fast. So there's a chemical potential that's for the excitons that's different at one end than the other?
Yes, yes. Well, if it's a superfluid phase, then the chemical potential difference will only drop at the contact, right? And that's, the driving force for the electron current in the electron layer. And the whole current just spontaneously responds to the drag. Yeah. Yeah. Okay. Yes, so perfect Coulomb drag over this range, and then zero drag immediately outside this range. Okay, I'll come back to this critical density later. The blue curve, let me just briefly mention that this is actually the tunneling current multiplied by 100 times, so that if you really look at this scale, there's negligible tunneling in this setting here. So we are in a pretty clean limit that we don't worry about artifacts from the measurement. So we can also do better. What I've been telling you is actually that we drive the electron layer and measure the whole layer, which is this kind of result here. This is from a different device. And we can also reverse the drive and the drag. And we can also drive the whole layer and measure the electron layer. And you get the same result. Over this window, you get perfect Coulomb drag. And then outside, you just get zero drag in the system. And even you switch which layer to drive or drag, you still get the same exciton current, because in this region here, the exciton current is only limited by the contact resistance of the entire double layer. So it should get the same exciton current in both situations here. Okay, so I hope this is convincing enough. And so to briefly cap, this is the phase diagram with VB and VG. And because of electron-hole interaction, that will pull down the electron-hole injection threshold, which is this line here, by an amount that is equal to the exciton binding energy. And within this triangular system, we have a charged insulating state, but there is a spontaneous fluid of excitons that's populated in the system. Okay, so let me do a couple of digressions here. So what is the temperature scale of this Coulomb drag? Here I'm plotting the drag ratio as a function of temperature at the field exciton densities. Let's just look at a couple of this curve here. At low enough exciton density, you can actually see that the perfect Coulomb drag lift to about 20 Kelvin in the system. So it's reasonably high temperature scale, especially if you compare to similar experiment in the quantum Hall regime performed in gallium arsenide double quantum wells. The perfect Coulomb drag is only observed below 300 milli-K. So it's about 2 orders of magnitude higher in energy scales compared to this double layer quantum well regime. Yeah.
How do you see a phase transition? It's like a crossover.
Yeah. this is more or less a two-terminal exciton resistance measurement that is again not sensitive to the BKT transition. So let me think, the drag ratio, now what I should plot is actually plot the exciton current in the system, better to plot the drive current to see whether, even in the two-terminal measurement, whether we can get any signature of exciton superfluidity. So it's limited by the contact resistance of the excitons, which is pretty large. So I doubt that we can, even we plot the drag current, we can spot a BKT transition. Probably not, I would say. So we actually need to do a 4-terminal exciton transport measurement in order to do that, which we are trying, but no success yet. Okay, and this frictional drag, I will come back to it immediately. Okay, and so let me just come back to this transition, this sharp transition from perfect drag to zero drag at this density. Actually, what's happening here is that with increasing exciton density, that was proposed by Mott in 1961, that there is an exciton-Mott transition, that at low exciton density, the electron holes are bound into excitons, but as you increase the pair density, at some critical density, you will go into a transition of this electron-hole plasma state. And the electron-hole plasma state pretty much just saying that the electron in the holes has zero binding energy, and as a result, you get a zero drag at low temperature limit. Okay. So we can study this Mott transition a bit more carefully by doing another experiment, that in this case, we still drive a current in the electron layer, but just measure the voltage in the whole layer in an open circuit. Okay. So this is called a drag resistance measurement. You flow current in one layer, but measure the voltage in the other layer. So the drag resistance is the voltage in this layer divided by the drive current in the other layer. Okay. So if you have a bound electron-hole pair at low temperature, you will just get infinite resistance, because this is an open circuit, the holes are not allowed to move, and as a result, you cannot really drive a current in the electron layer. So you just get infinite resistance. On the other hand, if you have an electron-hole plasma, the drag resistance will be proportional to temperature squared, because when you increase the temperature, there is more available phase space for the electron in the whole Fermi surface for Coulomb scattering near the Fermi surface. Okay, so let's look at the result. This is the drag resistance as a function of temperature. The different curves are different pair density. At low pair density, which are the blue curves here, you have excitons, and as a result, when you cool down the temperature, the drag resistance just diverge with decreasing temperature. And this dashed line is the Mott density, and below that density, actually above that density, then you can actually see that the drag resistance behave like a metal with a drag resistance scaling with a temperature square in a high density regime. Okay. So that's consistent with this Mott transition picture of increasing the pair density. You go from like an insulator behavior into a metal behavior at the critical density of the Mott density. All right. So furthermore, we can extract from this data this constant here, A. Yeah?
No, I was thinking, it looks like the boundary is 25 kilo.
Yeah, it's actually pretty close to 25 kilo ohm. Well, except here, this metal will really drop to zero, because it's a Coulomb drag. It's only sensitive to Coulomb scattering. Yeah. So you can extract the pair density dependence of this coefficient A here, and let's look at the result. The dots are the experimental result. 4 times 10 to the 11 is the Mott density here. You can actually see that the coefficient diverge near the Mott density with an exponent of about 3. Okay, so that's the scaling law for the A coefficient here. And people actually have done theory calculation assuming that there's no exciton. So in the purely frictional drag theory, you would expect that the coefficient A would scale as the pair density to the 1 over the pair density to the power 3, which is actually this black dashed line here. It would diverge towards the zero density. So you can see a very big difference compared to this theory which ignores excitonic interaction compared to the experimental data. So the experimental data is like as if the pair density just resets. Everything of the density you should just count from the Mott density here. So it suggests that there may be a quantum critical point at the Mott density that this Mott transition going from excitons to an electron-hole plasma may be quantum critical because of this divergence of the coefficient.
But certainly Mott's calculation assumed it was first order.
Yes, Mott thinks that it's first order because he thinks that the screening on the two sides are very different.
That's how he estimated the critical density.
Yeah, yeah.
But, what is the mobility difference between the electron and hole channel here? Like in these densities?
So they have nearly the same. So the turn-on density is similar in the two case, but the electron mass is about double of the whole mass. So the mobility may be a factor of 2.
I might be stuck on this, but I was also, I'm kind of surprised why 26 kiloohms matters. I mean, it wouldn't be relevant for the Mott criterion per se. But I was just wondering if once...
It's not exact.
No, but there's no disorder in this problem, in this theory.
But why would that land there? You're saying that's a coincidence, basically.
H over V squared.
But I thought that there's no theory for for a continuous Mott transition. I mean, if the transition is really continuous, there's no theory for this.
I was just wondering if that meant on the other side, the thing you're flowing into is as soon as you have coherent transport in the higher mobility channel, that's what's on the other side. So I don't know, I'm just confused with whether I should think of this purely as a Mott transition, right?
Did you measure several devices and they all show the same?
So this measurement is really just from one device, this kind of scaling. But for this kind of data, we have more than one device, yeah.
And they
Maybe
all show
similar, yeah. I mean, you get perfect Coulomb drag. You get perfect Coulomb drag here, and then the Coulomb drag just suddenly goes away, right? Yeah. This is set from multiple devices, yeah. Yeah. I think. I mean, you do expect, because of the perfect Coulomb drag data, you do expect that there is a transition from this to that, because you go from with excitons and without excitons. But I think what's a little bit surprising is actually that this scaling coefficient, I mean, this A coefficient here would actually scale and diverge at the Mott density in a way that looks like there's a quantum critical point at the Mott density. Yeah. Okay. All right. So with the remaining time, maybe a few more minutes, or how much time do I have?
Yeah, go ahead. Yeah.
Okay. Maybe in the remaining 5 to 10 minutes, I will just briefly talk about you can form an equilibrium trion. And so this is the phase diagram again, and I've been focusing along this red dashed line where the electron density is equal to the hole density. So this is the charge neutrality line. But because we have a gate, we can also add, we can also start from an excitonic insulator, which is this orange region here, and add extra hole doping or add extra electron doping into the system. So we consider the problem of doping an excitonic insulator. And it would be a very nice platform because it's a solid state platform for creating a Bose-Fermi mixture that's complementary to what the AMO community is studying. So the question is that when we add extra holes compared to the electron or extra electron compared to the holes, can we stabilize a equilibrium fluid of molecular trions, which is like a 3-particle bound states of 2 electrons bound to a hole or 2 holes bound to 1 electron. All right, so let me tell you another measurement method, which we actually perform a standard 4-terminal measurement in the tungsten layer, and while leaving the electron layer open circuit. Okay, so in this measurement, if there is no interlayer Coulomb interaction, then this 4-terminal measurement on the whole layer will be just the whole transport of the monolayer, right? There's nothing surprising. For instance, if it's in the electron-hole plasma regime with negligible interlayer Coulomb interaction in low temperature, that would just be the monolayer resistance. On the other hand, if you have some bound states formed between this whole layer and the electron layer, then you actually will get a diverging resistance at the low temperature limit because the electrons are not allowed to flow. So this is the result when we look at doping an excitonic insulator. This is again the compressibility map. This is the excitonic insulator triangle. And in this line, I'm also showing that the lines for the hole density is twice the electron density. And the red line is actually the electron density is twice the hole density. So P equal to 2N or N equal to 2P. Those are the two lines in this phase diagram. And this is the 4-terminal resistance measured with the geometry I just told you as a function of VB and VG in the same range. And you can actually see that in this triangle here, you get a very large resistance, although you have electron-hole pairs. The reason is that there is an electron-hole bound state, so you get an insulating state, and that's an excitonic insulator I've been just telling you. What's surprising is actually that there is this feature here, which is along the P equal to 2n line, that there is a very large resistance state also along this region. And you can make a line cut along this red dashed line, and you can actually see that on both sides, they behave like metal, meaning that the resistance just dropped with decreasing temperature. Only at this line here, the n is equal to P over 2 or P equal to 2n line, that the hole density is twice of the electron density. Only here that the resistance is diverging with the decreasing temperature. Okay? And so that actually can be naturally explained by the formation of tryons in the system. In this particular case, it would be the 2 holes bound to 1 electron, and we really form an entire fluid of tryons in the system. Because the electron layer, no current is allowed to flow. You just get an insulating state when you measure the resistance of the whole layer. Okay. Oh, by the way, similar experiment also from the Feng Wang's group, not that far away from here. And another experiment actually we can do is that there is a similar Mott transition for the tryons as like the excitons. So in this experiment, I'm measuring the resistance as a function of the tryon density, keeping at a density that P is equal to 2n or n equal to P over 2. All right, so at low tryon density, you can actually see that the resistance is increasing with decreasing temperature like an insulator. At some critical point here, once you pass this critical point, the resistance actually decreases with increasing temperature, behaving like a metal. So on this side, that means that actually that we have three particle bound state. We have a tryon fluid. On this side, the tryon fluids are all dissociated beyond some critical density, and it forms an electron-hole plasma. So this is schematic for this. We have tryon on one side. You increase the tryon density and go into an electron-hole plasma in this region. Finally, I will just tell you a little bit about, it's also quite a surprising finding when you start measuring the Hall effect in this tryon regime. Okay? So what we are doing here is still open circuit of the electron layer and measure the Hall effect of the whole layer. Okay? So this is the map of the whole layer Hall resistance as a function of temperature, and the gate voltage, which tunes electron and hole density imbalance. This is the position for the excitonic insulator. On the left side is forming holes. You're putting more holes into the system. On the right-hand side, you're putting more electrons into the system. The tryons form below about 6 Kelvin-ish, something like this. And let me show you 2 line cuts here along these 2 dashed lines. At very high temperature, the Hall effect actually of a whole layer just behaves like a normal whole layer, that you just get the density and the sign correct of a whole layer in this high temperature regime. But below the temperature that the tryons formed, you get, the red curve here would just go to a much higher Hall resistance. And what's even more surprising is actually that the Hall resistance of a whole layer would actually change sign, behaving like, you measure the Hall effect of a whole layer, it turns into like an electron layer. So it's quite surprising finding. And the only way that we can make sense of this data is, again, the formation of the tryons. Because in this case, you have an electron tryons. The 2 electrons will drag the hole to flow into the opposite direction, and that's how you get a change in sign of the Hall effect, even though you are measuring the Hall effect of a whole layer. Yeah.
Can you do quantum oscillations to measure the size of the Fermi surface?
Yeah.
Tryons are fermions.
Yes. Unfortunately, the tryons do not have high enough mobility, for us to start seeing quantum oscillations at low enough magnetic field. At high field, there are other complications I would love to discuss with you. We think that actually when the cyclotron energy of the electron and the holes become comparable to the tryon binding energy, it actually unbinds the tryon. So we are limited by a very small window that the cyclotron energy has to be substantially smaller than the tryon binding energy, and in that window we don't see quantum oscillation of the tryons.
Can you get closer to the white line? Can you quantize the red curve?
interesting question. But then that would be actually an even higher magnetic field. Then I think in that case we lose the trions. Yeah. So another experiment, just this is final slide, just bear with me, that you can drive a current in the electron layer and measure the Hall voltage in the drag layer. Maybe this is even cleaner because you see a drag that must be coming from the bound states between the two layers. So again, this is actually the Hall drag as a function of temperature and the electron-hole density imbalance. These are the two line cuts. You can actually see that you pretty much have zero Hall drag at high temperature because there's almost no drag. But once you form the Trion, on one side, you will get into a Hall drag Hall resistance, and the other side, you get the electron drag resistance. Okay, so this is, again, I think this is really, can only be explained by the formation of the Trions. All right, so here comes the conclusion that I hope I convince you that we actually can create an equilibrium exciton fluid in a system that exists perfect Coulomb drag to about 20K. We also can create equilibrium Trion fluid by doping an excitonic insulator at some particular condition, and we also can observe the Trion Hall effect in the system. So I think there are many interesting questions. Hopefully this platform can, open up an interesting way to study many of the physics that one can foresee in the future. For instance, whether we can probe exciton superfluidity, whether we can engineer the system to exhibit a quantum Hall effect for the excitons. And as Steve mentioned, whether we can see Trion quantum oscillation by improving the sample or even the Trion quantum Hall effect. Trions are fermions. They may be able to pair up as well at low enough temperature. Maybe there can be realized a Trion's superconductivity. And as well as so far, I have not told you anything about Moray. You can still imagine that maybe I can put one of the layers, replace the electron or the whole layers with a Moray lattice. Then we can start thinking about putting excitons in a lattice and then try to do something like the AMO community would like to do. So with this, thank you for your attention. Not too.
Thank you. I'll go.
Just a quick question. When you're following that n equals 2p line, what's the physics behind why that goes away experimentally?
Which goes away?
Yeah, basically why that doesn't continue out.
Oh, you mean basically why there is a Trion Mott transition at high enough Trion density, right? Why the Trions goes away? Because this is actually really like a line cut along this line.
Okay.
Yeah, so it's a Trion transition. We don't have a theory for Trion transition, Trion Mott transition. Yeah.
I'm biasing yellow. Please.
Could you please explain why the tungsten and the moly layers were used for the whole electron layers in the schematic rather than some other materials?
Oh, why just moly-selenide or tungsten selenide? So we want to choose a type 2 band alignment. So the conduction band is in conduction band minimum is one layer, valence band maximum in the other layer. You can actually choose other materials as well, like moly-telluride, the electron layer. That should also work. But we also picked this particular two because these two are the cleanest materials among the TMD family. So they have a very low density mobility edge. Yeah, yeah.
Okay, reluctantly.
I'm curious if you thought of putting the thing in the excitonic blocking state, so it's insulating, and then breaking them up with light. So a little infrared light should break up the excitons, and therefore...
You mean the excitons not flowing at all? Or,
you get the excitons flow.
Okay, but shine light to...
Break them up.
Mm-hmm. Yeah, that should work if we shoot like in the terahertz frequency, for instance. I think there's no...
Far infrared,
yeah, you probably shoot near far infrared and you can unbind them using light.
Well, yes, and if you did that, what you get is a conventional conductivity in the layers.
Yes.
So that would mean a switch to turn the effect on and off.
Yeah.
Hey, that would be a great detector, right?
Huh?
That would be a great RIR detector for you, right?
You're ahead of me. The point is that it should be very sensitive to light because of the blindness is a big effect. So.
Mm-hmm. I think at some particular frequency that hits the resonance of the binding. Yeah. Yeah.
Tony?
So I'd general questions. What are your thoughts about how you can actually probe for the superfluidity? So if I understood your talk correctly, you didn't have experiments that were necessarily very sensitive to superfluid state.
Okay, yeah. I have an answer. It turns out that it's actually not that hard. I don't know why the students still fail to do it. Maybe you also wondered, when I was a student. So you can think of it that each of these contact to to the hole and the electron, this pair of contact is an exciton contact. So you have a 1 exciton contact here, 2 exciton contact. You have 2, you can flow an exciton current, but then there are some chemical potential drop at the contact. But if we can actually put 4 of this contact here, and we measured basically the displacement field gradient in each of these contacts. Let's say we add 2 other probes, 4 more contacts, 2 other probes. We measure the interlayer voltage difference at this location and also measure the interlayer voltage difference at this location. And if this voltage difference is the same on the 2 locations when there is an exciton current flow, and that should be a definitive proof of exciton superfluid. So we know the answer, but we failed to do it yet.
Can you do the counterflow measurement that Jim Eisenstein did?
I mean, this is a counterflow measurement, right?
Yeah, so just connect around,
Oh, you mean a series counterflow?
Yeah.
Yeah, this is a drag counterflow. To do a series counterflow, the problem is actually that we haven't figured out the way how to do it because we need to apply a bias voltage between these 2 layers to actually create a fluid of excitons. So if we can figure out, well, I think...
You said just put a gradient of the it's a dipole. So
Yeah. So there are some complication here because we need to apply a bias voltage between these 2 layers to do a series counterflow like what Jim Eisenstein did. We have to actually connect the electron and hole layer outside. But then at the same time, we need to maintain a bias voltage between. So that actually makes it hard. Yeah.
So first place, one little question. When you plot the resistance, was that ohms per square or ohms?
It's pretty close to ohm per square, the geometry of that, yeah.
So just a comment, we proved a theorem a while ago that you can't have a first order transition with dipolar interactions. Whether that's relevant here, I don't know, but there is a reason for the Mott transition for dipolar interactions to turn continuous, probably with intermediate phases. And that may or may not be relevant to your experiment, but...
Yeah, so that's for dipolar interaction.
Which this is.
Yeah. But near the Mott transition, it may be more complicated than just the dipolar interaction, right? Because the excitons, the ball radius becomes pretty big, right?
Not self-consistently. If you assume that it's a first-order transition, the Bohr radius stays constant up to the transition and then jumps. So anyway, it's a little complicated, but probably that's not an issue.
Okay.
Yeah, just a quick question. Why does the contact limit the exciton current?
Why this? So this is a 2-terminal measurement. So like a 2-terminal superconductor, let's say, in order to flow a supercurrent, the voltage, you still need to create a finite voltage difference between the 2 contacts because there's a voltage drop at the contact. So that's more or less like here, Even though the exciton may be a superfluid state, in this 2-terminal measurement, you still get the potential drop of the exciton at the contact. And that, would just give you, if let's say that the exciton is really in a superfluid state, then the exciton resistance in this 2-terminal measurement would just be equal to the exciton contact resistance.
How about this? Why don't we migrate the discussion to the reception out in the courtyard? So thanks very much, Fai.
Thank you.